Welcome to The Explainer. This is where we break down big topics into ideas that just click. Today, we're going to talk about sound. Yep, everything from that echo you hear in a canyon to the beautiful note from a guitar. So, you ready? Let's get into it.
All right, so let's kick things off with something I bet you've experienced firsthand. And from there, we'll start to unravel the incredible science behind what you're hearing. You know that feeling, that kind of ghostly reply you get? Well, that's an echo. And nope, it's not magic, it's pure physics. And honestly, it's the perfect way for us to start digging into how sound waves actually move around and bounce off things. So what's an echo, really? Well, at its heart, it's just a sound wave that's bounced back at you. Think about it like throwing a tennis ball against a wall. The sound shoots out, smack, hits a big, hard surface, and then comes right back to your ears. But here's the catch. For you to actually hear it as a separate, distinct echo, a couple of things have to be perfect. And this is what I find so cool. These rules are super specific. That 17-meter number, it's not just pulled out of thin air. See, our brains need about 1/10 of a second to tell two sounds apart. So scientists figured out that at the speed of sound, the wave has to travel at least 17 meters and back for that delay to happen. Any closer, and your brain just mushes it all together. It's not an echo anymore, it's just reverb. Okay, so this whole echo thing isn't just a fun party trick in a canyon. It's an absolutely critical tool in both nature and technology. Bats, for instance, are the masters of this. They use these high-frequency echoes to literally see in total darkness. And guess what? We totally copied them. We developed SONAR, which does the exact same thing, but underwater to map the ocean floor. It really is all about just sending out a ping and listening for the bounce back. Okay, we've talked about the big picture, sound waves bouncing across huge canyons. Now let's zoom way in. To really get what sound is, we have to look at where it all begins, these tiny invisible movements. Because here's the bottom line. Every single sound you've ever heard starts with a vibration. So this slide perfectly shows the difference between vibration in a perfect physics textbook world and, well, the real world. In a vacuum, with nothing to get in the way, a natural vibration would just keep going and going forever. But out here in the air, you've got resistance, right? That acts like a brake. It's a damping force that saps the energy from the vibration until it just fizzles out. But what if you don't want it to stop? What if you decide to interfere and keep giving it a little nudge over and over to keep it going? Well, that's what we call a forced vibration. You're basically taking over and making the object vibrate at your rhythm, not the one it would naturally choose. So, here's the main takeaway. It all boils down to the forces at play. If you just hit it and leave it alone, that's natural. If it's vibrating but rubbing against something like air, that's damped. And if you keep pushing it to a beat, that's forced. Simple as that. Okay, now we get to a really special, almost magical case of forced vibrations. This is where things can get intense. The phenomenon is called resonance, and it is a game changer. I know, it sounds like something out of a movie, right? But a bridge collapsing from a sound wave? It can happen. And the crazy thing is, it has nothing to do with how loud the sound is. It's all about its frequency. This is where you see just how powerful resonance can be. You know, the absolute best way to get this is to think about pushing someone on a swing. If you just run up and shove it at random times, it's awkward, right? You don't get much height. But if you time your push perfectly with the swing's own rhythm, pushing just as it starts to move away from you, it'll go higher and higher with barely any effort. That perfect timing, that sweet spot, that's resonance. So this is the secret sauce, the one and only rule for resonance to happen. When the frequency of your push exactly matches the object's own natural happy frequency, boom. The energy transfer is off the charts, and the amplitude, how big the vibrations are, just explodes. And once you know what to look for, you see this stuff everywhere. You know why soldiers are told to break step and just walk normally over a bridge? It's to avoid having their marching rhythm accidentally hit the bridge's natural frequency. When you tune an old-school radio, you're literally turning a dial to make your radio circuit resonate with the broadcast frequency of the station. And yeah, that annoying buzz in your car that only happens when you hit like 65 miles per hour, you guessed it, that's resonance. All right, so we've established that all sound is just vibrations. But how does our brain translate those simple wiggles into the rich world of sound we experience? How do we tell a whisper from a yell, a high squeak from a low rumble, a piano from a guitar? Let's crack that code. First up, loudness. This one's pretty straightforward. It's basically how our brain interprets the power or energy of the sound wave. A big wave with a big amplitude has a lot of energy, and we hear that as a loud sound. A tiny wave with a small amplitude, that's a quiet sound. Easy enough, right? Okay, next is pitch. This is what makes a sound high or low. And pitch is all about frequency, how fast the vibration is. Super fast vibrations give you a high-frequency wave, and that's a high-pitched sound, like a piccolo. Slow, lazy vibrations give you a low-frequency wave, and that's a low-pitched sound, like a big bass drum.
And last but not least, we have the most interesting one, in my opinion, quality, or as musicians call it, timbre. Think about this. If a violin and a trumpet play the exact same note at the exact same loudness, how do you still know they're different? That's quality. It's like the unique voice or fingerprint of a sound. So this right here, this is the decoder ring for sound. It's the direct link between what you hear and what's actually happening physically. Loudness, that's just the wave's amplitude. Pitch, that's its frequency. And that mysterious quality, or timbre, it all comes down to the actual shape of the wave, what we call its waveform. And this is where it all comes together. That final piece, the waveform, is what separates a beautiful melody from just noise. Music comes from nice, regular, repeating patterns, predictable waveforms. Noise? It's just a messy, irregular, chaotic jumble of waves. In a way, it's the sonic difference between order and chaos. Okay, you've soaked up all the physics, so how about we test that knowledge? Let's do a couple of quick questions to see how all these ideas really connect out there in the real world. Okay, let's think this through. We know every big structure, like a bridge, has a natural frequency it likes to vibrate at. So what happens if you get a whole bunch of soldiers marching in perfect time, creating a rhythmic pushing force? If their marching beat just happens to match the bridge's natural frequency, you get resonance. And those vibrations could build and build until they become incredibly dangerous. All right, let's break this down. Same note means they have the same frequency, so it can't be pitch. Same loudness means they have the same amplitude, so it's not that. So what's left? It has to be that unique sonic fingerprint, their quality or timbre. It's all because the shape of the sound wave from a violin is totally different from the shape of the wave from a piano. And here's a final little thought to leave you with. If music is just orderly, regular vibrations, and noise is just chaotic, irregular ones, what does that say about us? Maybe our love for music and our hatred for, say, the sound of nails on a chalkboard is really just our brain's deep-seated preference for order over chaos. Kind of makes you think, doesn't it? Maybe deep down, we really are all just looking for a good vibration.